Good evening, everyone. My name is ZAID MUSA, and I'm presenting on the optimization algorithm to reduce training time for deep learning computer vision algorithms using large data sets with tiny objects. So the problem statement for this research is, number one, detecting objects in large images requires a lot of computational resources. So here we see an object or an image captured, let's say, for example, by the surveillance camera, and then you have a lot of objects. So to be able to detect all these objects at once requires high computational resources like processing of the system. Another problem is existing methods reduce cost but often reduce detection accuracy. So let's say you have an input image here. This is just for illustration purpose. This might not be the real image. So let's say you have an input image here. You will try to apply some features to be able to resize the image or to reduce the quality. But at the end, you end up having something that would affect your detection accuracy, which is a problem as well. Next, we have small objects are easily affected when images are resized. So let's say you have this object here, this image here, with a lot of objects on it. So this purple color you're seeing is like the label of the object. So if you now reduce the quality or you try to resize this so that you can be able to have a faster training time, it would affect the detection accuracy as well. So slow and expensive training limits how widely these systems can be used. Just as we have said, when you have a lot of computational resource, it tends to be expensive, and at the same time, in some cases, it tends to be slow, especially when you do not work on the input to the system. The motivation for this paper, it focuses on drone applications. Drone images contain many objects, just as we have seen with some of the images, which makes detection challenging. So to be able to overcome the detection challenge and also reduce training time is what this paper proposes. So another point is accurate detection is important for making correct real-world decisions, just as we have seen. If you're able to detect accurately without errors, it is very important when it comes to real-world applications. Many systems also need to detect objects quickly in real time, let's say like surveillance or security-based applications. When they're able to detect objects quickly, it is very, very important to make decisions. Improving efficiency can enable wider adoption in real-world environments. If you improve efficiency of your system, it will be able to be used in a lot of applications. So the proposed solution, a pre-processing algorithm is used to reduce data set repetition. So what happens is, let's assume this is an image. So what the pre-processing algorithm does is it just considers the important part, it brings it out, and this is what we call a keyframe. It considers a frame around the important object and it discards the remaining part of the image. So this is like a typical example of where it is used. It mostly works with sequential images. Sequential images are images captured with drone. So in this scenario, you see a lot of cars here, and you also see this red box. This red box is more like the images of these buildings and the rest, which we do not need, but it keeps on showing in our videos. So the pre-processing algorithm discards this part and only focuses on this part, while still trying to maintain the object resolution. Here also you have, let's say, vehicles coming on the road. The entire space here are things we do not need. We only need this part. So you have these objects here, which are the blue and the red, and these are your keyframes as usual, and then it discards the rest, which is called redundant data. So this is a typical analysis or an application, a real-life application where it was conducted on the paper. So as you can see here, these cars are parked on the road while these three are moving. So this is like a snapshot from the video. You have this car moved, as you can see it here. This same car moved, as you can see it here, while this one also moved, as you can see here. So what this does is, it only considers these places where you have the red circles, while it discards, even when it comes to when you have the same objects within a video, it will discard the ones that are stagnant, because it sees them as repeated data and only focuses on the ones that are moving. So So that's why I said sequential data. So the result of what happened, for this pre-processing algorithm, the result is when they did it, you have 3 different types of data sets that were used, and significant reduction in training time was achieved while detection accuracy was still remains comparable. So you have 87% from drone data set. There's a data set that was compiled in Spain. These 2 are from Spain, while this one is from a China data set. So they had 87% reduction in training time. Here they had 72% reduction, while this one they had 76% reduction in training time, while still maintaining detection accuracy. So from the insights, what we can notice is performance improvement depends on the type of data set. As you can see, the percentage is not the same, but there is an improvement with respect to the data sets. So the method works for sequential image data. So as you can see, as well from the real life scenarios and examples I showed, you have sequential image data is where you have videos, and then you take like as many snapshots as possible from those videos. Inconsistent labeling can reduce accuracy. This was while they were conducting the experiment. In some cases, you have a data labeled as maybe a car, and then the next one you have it labeled as a vehicle. So when you have that, it can reduce the rate of detection accuracy as well. And the method performs well across different data sets, as we have seen. From the previous. You have seen different data sets that were used: the drone, the roundabout, and the visitor. So in conclusion, the method significantly reduces training time, as we have seen from the percentages. The detection performance is still preserved. Redundant data removal improves efficiency, as we have also seen. And this is suitable more for drone and surveillance related applications.